Hi students, today we'll discuss a very interesting SHM problem. The problem says that this is Earth of radius r, and here is a simple pendulum whose length is comparable to Earth's radius, and the bob is grazing the North Pole. So if we slightly displace this pendulum bob, what will be the time period? The simple pendulum has length L. Remember that in case of simple pendulum, the oscillation that it will perform will always make an angle less than 4 degree with the vertical or with the initial position. So what we'll do is that we'll slightly disturb it. Another information that you must know is that a simple pendulum performs both SHM, both kind of SHM. It performs linear SHM as well as angular SHM. Let us assume that the angle obtained by the pendulum with respect to vertical is theta. And also the bob makes an angle phi with the radius, with the vertical radius at the center of Earth. This angle is phi. So gravity for this bob will act towards the center. So this is the gravity. Okay. We'll extend this line. Now we need to find out the torque of mg about the point of suspension. Let me call the point of suspension as A. So to get the torque, we need to draw the perpendicular line, right? So we'll drop a perpendicular from the point of suspension to the vector mg. So this is the red line. Now what is the value of this line? So this radius is r, this angle is theta, this is phi. So you can easily see that sum of interior angle is the exterior angle. So this angle is theta plus phi. So what is the perpendicular distance? It is coming as L into sine theta plus phi. So what will be the torque of mg about the point of suspension A? So that's going to be mg into L sine theta plus phi. Now because both the angles theta and phi for a simple pendulum will be very small, so we can assume that these angles are extremely small and the torque tau with a negative sign, because the theta, you can easily see this theta is in the anti-clockwise direction and the torque is in the clockwise direction. So there has to be a negative sign showing that the displacement and the torque are in opposite direction. So approximately, because both the angles are small, we can write theta plus phi using the approximation sine theta approximately theta. Now we'll do what? We'll take theta out. Why I'm trying to take theta out? Because of the simple reason that in case of SHM, we need to find tau proportional to minus theta, where theta is the displacement with respect to vertical. So if I would have taken phi out, then the torque will obviously be proportional to phi, but the theory says that the torque has to be proportional to the angular displacement with respect to the mean position, and that is theta and not phi. So this is the torque and this is an unbalanced torque. Now what is the value of phi? Because both the angles are small, so tan phi will be approximately phi, and the value of tan phi from this diagram, we can easily see that if I call this line x, then what is tan phi or phi? It is coming as x by r. And what is tan theta? Tan theta, approximately theta, is equal to x by L. So we'll put both of these values of x by r and x by L of phi and theta respectively into this equation. So we'll get the unbalanced torque tau is equal to minus mgl into 1 plus phi. Phi is x by r and theta is x by L into theta. We'll cancel the x, we'll get the torque as minus mgl into 1 plus L by r into theta. Now, because this torque is unbalanced, so we can write this torque as I alpha. What is the moment of inertia of the simple pendulum bob about the point A or point of suspension? Because the bob is a particle, we can assume I as ml square alpha. So we cancel the m and we got alpha is equal to g into 1 by L into 1 plus L by r into theta. So if we multiply this 1 by L into the bracket, we get alpha is equal to minus g into 1 by L plus 1 by R into theta. So this is equal to minus omega square theta. So what is omega? Omega is coming as root under g into 1 by L plus 1 by R. So this will be the angular frequency of a simple pendulum whose length is comparable to R's radius. Now, what will be the time period of this pendulum? The time period of this pendulum t is equal to 2 pi divided by omega. This means the answer is 2 pi root under g into 1 by L plus 1 by R. For your JEE, I recommend you to memorize this answer. And the process also is interesting to build concept. So if you remember this, the problem may ask you that what is the time period of a simple pendulum whose length is equal to that of the arc's radius. So if we put in this formula, because you already know the formula, as I told you to remember it, to memorize it. So you put L equal to R. So what is the answer that you are getting? 2 pi root under G by 2R. So this is coming as root under R by 2G. So if there is a simple pendulum whose length is equal to that of the arc's radius, what will be the time period? That's the answer. And the pendulum not only should hang at the North Pole, it can hang anywhere on the Earth's surface. The condition is that the bob must graze Earth's surface. So I hope you really like this solution. Thank you for watching.